Hello! In this video, we will be solving an integral which I found in a Facebook group called David's Integrals. I'm leaving the exact link for that post in the description below. So the integral is the integral of sine x minus x from 0 to 2 pi. So the definite integral, or the indefinite integral case, by itself is quite hard, and I don't think I can solve this by hand, nor can I found this in terms of elementary functions. However, the definite integral from 0 to 2 pi seems a little bit simpler than the indefinite case. Why? Because I have something limits from 0 to 2 pi, and for some reason I feel like I can exploit some identities for this one. So for this video, I will be presenting two solutions for this. The first one is using what I call the symmetric substitution. I'm not really sure how people call this, but I'd like to call this a symmetric substitution because with a substitution, I'm trying to exploit the potential symmetry of the integrand on the interval AB, with A and B being the limits of integration. So the substitution I'd like to make is u is equal to a plus b over 2 minus x. Essentially, that's the average of the limits minus x. So the limits of the integral becomes b minus a over 2, that's the upper limit, and then the lower limit is a minus b all over 2. Of course, this assumes that the integral is integrable in the interval ab. Note carefully that the limits of the resulting integral is in the form negative k to k, where k is equal to b minus a over 2. With that gives me some sort of idea that I can use some properties for the evenness or oddness of the function. So remember that a function is odd if f of negative x is equal to negative f of x. This gives a graph that is symmetric with respect to the origin. On the other hand, a function is even if f of negative x is equal to f of x, and its graph is symmetric with respect to the x-axis. So, that alone is not useful, but with some known properties of integral of odd and even functions, we can do wonders for solving definite integrals. In particular, the integral of an odd function from negative k to k is equal to 0, while the integral of an odd function is equal to twice the integral of 0 to k for the same function. So, I'm hoping that at some point in my solution, I'll end up with either of the two forms. Let's try to use the substitution first. So let's use the substitution u is equal to pi minus x. Pi is equal to the average of 2 pi and 0, which are the limits of the integral. If I do that, we'll get limits from pi to negative pi, and then we have the derivative du. It's the negative du, because du is equal to negative dx. The integral then becomes sine pi minus u minus quantity pi minus u. Of course, we can take out the negative sign in the differential and then put that in the limits so that we can interchange limits from negative pi to pi. Now we can use the property for sine, specifically that sine pi minus theta is equal to sine theta. So the sine times pi minus u is simply equal to sine minus u, sine u. And then the quantity of negative pi minus u becomes negative pi plus u. Again, if we do some rearranging of this one, we can factor out the negative, so that's negative pi minus the quantity of sine u plus u. And then using another property of sine, that sine of negative u or negative theta is equal to negative sine theta, I can factor out the negative outside. So the integral becomes sine of pi minus a quantity of sine u plus u. Again, if you use the property sine pi minus theta is equal to sine theta, the integral reduces to sine of sine u plus u. Still the limits from negative pi to pi. So for the past 6 lines, we are just exploiting some properties of sine. Now we end up with something quite similar to the first integral. So suppose the integrand now is g of u. So that's g of u is equal to sine of sine u plus u. We'll try to check if that's even or odd. Why? Because we have something, we have the limits in the form negative k to k. So as I've said a while ago, we'd like to exploit that possible property. So let's check that g of negative u is equal to sine of negative u plus negative u. Since simplifying that gives sine of negative sine u minus u, using again the property that sine of negative theta is equal to negative sine theta. If I factor out the negative in the argument of the sine, that's negative of the quantity sine u plus u. Using again the property of sine, I've been repeating myself all over, but that's how it is. That becomes negative of sine u plus u, which is negative g of u. This means that g of u is odd, and therefore the integral of g of u from negative pi to pi is 0. Therefore, the integral we're looking for is 0 because it's an integral of an odd function. So it's quite a long way, but the process is quite repetitive, just a series of application of the properties of sine. Now let's look at an alternative solution. For the second solution, we'll exploit a property known to many as the King's property of definite integrals. I'm not sure how people call it, but I've seen online people calling it King's property. Personally, I'd like to call it the linear property of definite integrals. In any case, the statement is that the integral of f of x from a to b is equal to the integral of f of a plus b minus x from a to b. So essentially, you are replacing the argument of the function inside to a plus b minus x. You can easily verify that by simple substitutions. Applying that to the given integral, so the integral becomes, or the integrand becomes, sine of 2 pi minus x minus 2 pi minus x. We replace x with 2 pi minus x by the King's property. Next, using the property that sine of 2 pi minus theta is equal to negative sine theta, the first term in the argument reduces to negative sine x. And then the whole argument becomes negative sine x plus x minus 2 pi. Next, if I factor out again the negative 2 pi, I isolate the 2 pi, similar to the step a while ago, that becomes sine of the quantity negative sine x plus x minus 2 pi. Using a similar property as a while ago, that sine of theta minus 2 pi is equal to sine theta, the integrand reduces to sine of negative sine x plus x. We can factor out again the negative in the argument for sine to give us the negative of the quantity sine x minus x. Why would I want to do this? It's because I want to have something similar to the integrand in the original expression, which is sine x minus x. Next, we again use the property of sine, that sine of negative theta is equal to negative sine theta, to give us a negative of the integral of sine x minus x. That looks very familiar because the negative expression is the original integral we have. So if we let I be the original integral, we have I is equal to negative I. If we solve for I, that gives us I is equal to 0, which means that the integral of sine x minus x from 0 to 2 pi is equal to 0, which is similar to what we got in the first solution. So just to show you the graph of sine x, or sine of sine x minus x from 0 to 2 pi, it looks like this. It looks like a common sine, and that it's quite symmetric with respect to some point in the middle, and that's the point pi 0. So that means that the area below the first interval from 0 to pi is equal to the area above the x-axis from pi to 2 pi, which definitely means that because the areas are signed, meaning the first one is negative and the other one is positive, the sum of the two will be 0. Yes, yes. So that's it for this video, and thank you for watching. If you like this video, please like and subscribe. Thank you.